Okay, I'm going to write up this solutions to this worksheet for you. Try to stay in frame. So we've already talked quite a bit about the notes here. Believe it or not, I'm gonna come back to this one. All right. The other two, I should probably change the order here a little bit. Talk about network. Let's take a look at 2 and 3 first. Then I'll go back and do number 1. So an applied force does 400 joules of work on a 50 kilogram box sliding across the floor. Friction also does work in the box, stealing 150 joules of energy from the box. So net work done on the box. Well, the net work being done is a combination of the work due to any applied forces and the work due to friction. Now, it doesn't tell us anything about the applied force, direction, nothing. It's just telling us how much work is being done by each force. So we don't need to worry about the direction at all. We know that the applied force is putting in 400 joules of work. Friction is always stealing work. Now, whether or not you want to think of that as plus negative 150 or minus 150, doesn't matter. The end result is that the net work done on the box is positive 250 joules. The direction of the forces only matters in that, trying to figure out whether or not the force is adding to or taking away energy. Now, I guess this means starts from rest. Right? It doesn't specifically say, but we have to make some kind of assumption there. Oh shoot, I gotta pause this and take attendance. Hold on a second. Oh, whoops. Alright, so back at it here. So, if the box starts at rest, determine the final velocity of the box. Alright, so work is changing kinetic energy. So changing kinetic energy equals the net work done equals plus 250 joules. Alright, let's assume it starts from rest. Alright, so as we talked about in class, changing kinetic energy has to be written as KE final minus KE initial. Now, I should have written capital K here to be consistent with the AP naming scheme, but we'll stick here. KE initial in this case is 0. Alright, remember, you cannot write 1/2 m delta V squared. So plus 250 joules equals 1/2 of 50 kilograms times V final squared. So 2 times 250 divided by 50, square root of it, that's going to give us V. Alright, I just did this in class, but I don't remember it. Oops, that's not right. Forgot my parentheses. That's about 3.2. Alright, there we go. Next one here. When a 10 kilogram object is dropped and falls 10 meters, the Earth does positive 1,000 joules of work on the object. Alright, it's got to fit in there. Determine the change in kinetic energy of the object. Well, change in KE must be plus 1,000 joules, right? And if I think about the bar graphs, okay, PEG, if I look at PEG and KE as it falls, right, falls down, alright, if it's gained 1,000 joules of kinetic energy, right, if that's 1,000 joules, that means it must have lost 1,000 joules of gravity. So delta KE's change is plus 1,000. Delta PEG's, I should call it UG, should have called those UG, is negative 1,000 joules. Alright, so that brings us to a result here. So what we get from that is delta KE it always equals, well, I shouldn't say always. It's always equal to negative delta UG, or delta PEG in this case. The problem is if there's internal energy factored in, right? I really should be saying just delta U. I should leave off the G. I should really be saying delta K equals negative delta U. And this could be a combination of U internal, UG, US, and so on. The only thing that's a little weird here is, anyway, the internal gets very strange in this thinking. And that's going to bring us to a later concept. So this is kind of the full work energy theorem. So at the end of the day, it's kind of you can also report work net as delta U, or F dot R as negative delta U. That's kind of the important one there. Alright, it's going to turn out that the integral of force with respect to position equals change in, negative change in potential energy. But we'll get to that later on. I'm going to go back and look at number 1 now. Alright, let's say, okay, so we've got a rope pulling on a box, 3 kilograms, force of 50 newtons at an angle of 25 degrees. Displaces at 8 meters across the table. Determine the work done by the rope on the box. So this is practicing with that dot product, right? Work is equal to force dot delta X. Alright? So our force here, right, if we draw a force diagram of this object, it's kind of helpful. We're going to need it later on anyways. So we actually have more forces, Fn, F, and Fg right now, right? And this is 25 degrees. So what I need is, what would be called Fx, right? And there's also a y component to this force, Fy, the way I drew it here. So the x component of the force is parallel to the displacement, delta x. So the work is going to be, the way we talked about is the magnitude of the vector, which in this case is 50 newtons, alright, times the magnitude of the displacement vector, well, which is positive 0. It's not really the magnitude. We want the positive sign in there. Times the cos of the angle between them. Alright, so 50 times 0.8 is 40, times the cos of 25 gives us 36 joules. So that rope adds 36 joules to the box, which means K final is 36 joules. Alright, work is change in energy, remember? Alright, K initial, it doesn't say it up here, initial. This was a brand new worksheet, so I gotta go back and edit a few things to it. Initial velocity, let's assume was 0. Alright, so it's gaining 36 joules of kinetic energy, therefore final kinetic energy is 36 joules. Now we're going to change things up, okay? We're going to add in a frictional force. Alright, so work done by friction, I'm going to leave myself some space here. So work by friction equals the force of friction times the displacement times the cos of the angle between friction and the displacement. Alright? So let's draw another force diagram here. Well, yeah, let's draw a new one. What the heck? We're going to have Fx, the two components of this angled force, Fy. Those are really important, so I'm drawing those first here. There's F. There's Fg. Here's Fn. and now we're going to have force of friction. All right, so the force of friction is the coefficient times the normal force. All right, coefficient times the normal force. But what's the normal force? The normal force is not 30 newtons. That's the force of gravity. Normal force, actually, we have to look at the vertical direction here, right? Fn and Fy have to add up to equal the force of gravity. Right, so we need to kind of do a little side calculation here for the normal force. So Fy plus Fn minus mg have to be equal to 0, or Fn, oops, got a little crazy, Fn has to be equal to 30 newtons minus 50 newtons times the sine of 25 degrees. We need to find the y component here. All right, so bring that over here, bring that over here. We get 30 minus 50 times the sine of 25, and that's about 9 newtons, or 8.9 newtons. All right, I'm going to just make it about 9 newtons to call it good, because, you know, I guess I better call it 8.9. So Fn is about 8.9 newtons. All right, so now we can kind of put it all together here, right? 0.2 coefficient, no dimensions. Fn is 8.9 newtons, not very big. All right. Cos of the angle, well, let's get delta x in there first. Displacement is still 0.8 meters. Theta, what the heck is theta? Well, here we go. Delta x is to the right, friction is to the left. The angle between those two vectors, this is a vector diagram, not a force diagram, is 180 degrees. Actually, I should probably make it that way, right? It's positive 180 degrees or negative 180 degrees. Doesn't matter. And what that gives us is a negative sign. So the work done here is negative because these two vectors are pointing in the opposite direction. So it's pretty neat. This is not a vector diagram or force diagram. It's a vector diagram. So put it all together. 0.2 times 8.9 times 0.8 times the cos of 180. I'm going to type it in there. It's going to give us a work done to friction. Work due to friction equals negative 1.4 joules. So there's our final answer there. Now the net work done in the box is just like what we did in one of those later problems here. So work net, it's equal to the work by the force plus the work due to friction. All right, so in this case, it's not a drastic difference. So positive 36 joules from the applied force, negative 8.9 joules from the, negative 1.4, darn it. It's like, wait a minute, that's too big. 1.4, the 8.9 was the force of friction. So 36 minus 1.4, what am I typing that into the calculator? 34.6 joules. Now, you know, I'm going to change this problem. I'm going to make the coefficient larger. I'm going to make it like 0.6. All right? So 0.6 times 8.9 times 0.8 is 4.2. See, even that's kind of low. Maybe I'll make the mass bigger. Maybe I'll make it a 30 kilogram box. No, that would be too big. Then the force of friction would be too big. I don't know. Don't want it. Force friction would be all right. 30 kilograms. Maybe not. Anyways, work net 34.6 is our change in kinetic energy. It's positive. So delta K is positive 34.6 joules. So that equals 1/2 mv final squared minus 1/2 mv initial squared. That one goes to 0. So V final equals the square root of 34.6 times 2 divided by 3.0 kilograms. Square root of 2. Am I off the page? No, thank God. 2 times 34.6 divided by 3 gives us 4.8. All right. Hey, that line there is terrible. I apologize for that. All right. Let's go over to the next page here. All right. So, at the end of the day here, we can look at this from a functions perspective as well. So, a little bit different. Force versus position graph. So position varying forces are quite common. In fact, most of the forces we see are actual in nature, are actually position varying. They depend on the physical nature of a system, which affects the space around it. For instance, gravity. Right? Close to the Earth, we approximate gravity as just being mg. But really, gravity is the attraction between two objects is g, big G, m1, m2 over r squared. So it is position varying. It's proportional to 1 over r squared. Same thing with electric force, right? 1 over r squared dependency. So it's spring force, right? Linearly dependent to position. So 5 kilogram object. First problem is just constant force, no position dependency actually, just to kind of build an idea of what's going on with this graph, okay? So determine the work done by the force of the object and the final speed of the object. So the work done on the object, it's force times distance. So if it's just a constant force, it'd be 6 newtons times 2 meters, which actually is indeed the area under the curve. So area under force versus position is work. So work equals base times height equals 2.0 meters times 6.0 newtons. You get 12 newton meters, which is 12 joules. So therefore, change in kinetic energy is 12 joules positive. You do have to be a little bit careful, right? This could actually go negative as well, right? You could have relative 0. So their displacement, right, depends if you're going from 0 to 2 or from 2 to 0. We say we're going from 0 to 2.2, right? So we're going that way, it's positive. If we were going the other way from 2 to 1, you'd actually have to make this work done negative, which is hard to know from the graph, but when you do the calculus and integral, it's actually quite easy. So to move from 0 to 2, it's positive force, positive displacement, positive work. All right, so we're going to gain energy, and that's going to equal 1/2 mv final squared minus 1/2 mv initial squared, which again, this is 0, starts from rest. All right, so v final is going to equal the square root of 2 times 12 divided by 5.0. Second square root of 2 times 12. Oops, I keep forgetting my parentheses. My other calculator automatically puts parentheses in there, so I've been forgetting it on this calculator. Equals 2.2 meters per second. Cool result. Here's the same 5 kilogram object going from 0 to 2 meters, but now we have a nonlinear force. So, from 0 to 2.2, so the work here is 1/2 base times height. So work equals 1/2 of 2 meters times 9.0 newtons. 2 times 9, okay, you get work equals plus 9 joules. All right, so 9 joules equals 1/2 mv final squared. That's 0, so I'm not going to write it. So 2 times 9 divided by 5, square root equals v final. V final equals radical of 2 times 9 divided by 5 is 1.9. 1.9 meters per second. All right, pretty cool, pretty cool. So you can get the area under the curve, set that equal to the, this reminds me a lot of impulse, right? Force and time impulse was. So you gotta be careful. Now, of course, then we have to deal with nonlinear position functions. And this is pretty cool. You know, we've said that force times distance equals change in kinetic energy or work. When we make a differential equation, the first thing we always do is replace any deltas with d's. All right, replace any deltas with d's. So that's what we did here, replacing both the d's. And then, just like in algebra, whatever you do to one side, you take the integral of each side. We have integral of f net with respect to r equals change in kinetic energy. How did I get there? That's an interesting one. This one was like integral of 1 times dk, right? Which ends up being k evaluated from, well, what? It's position 1 to position 2. So, you know, from 1 to 2, location 1 to location 2, kinetic energy initial, the kinetic energy final, k initial, k final, you get delta k. Kind of a, not delta x, kind of delta k, that's the integral of 1 dk. So we define work now like this. We say work equals change in kinetic energy. Sometimes they like to throw the negative delta u in here instead of delta k. Right? F integral force with respect to position. And we just get right into it here. You know, we have a force function, non-linear. All right, 20 centimeters is x. So it's going to go from 0 to 0.2 meters, our limits. All right, so work is the integral of force with respect to position. In this case, it's x, it's one-dimensional. All right, so work, and it's going to be from the limit of 0 to 0.2 of 350 x squared dx. So finally, we have a dx, not a dt. All right, you got to be careful here because you can't confuse this with momentum. All right, so put in 0.2 up there. 350 times 0.2 to the third divided by 3 equals 0.93 joules of work's being done here. All right, so the force you'd have to apply you'd have to put in 0.93 joules to compress it. Then when you release it, you're going to get that 0.93 joules into kinetic energy. So 0.93 is 1/2 mv final squared. M is 0.2, so v final equals the square root of 2 times 0.93 divided by 0.2. Second square root of 2, 3 divided by 0.2. Oh no, syntax error. What did I do? Second square root of 2 times 0.93 divided by 0.2, 3.0. So we just take the integral. Rather than having the graph, we take the integral of the function with respect to time. All right, we got one more here. All right, just going to wrap this up here. An object of mass 0.1 kilograms moving along straight lines, subject to the following position versus time. Force. Quantitative sketches force from 0 to 1. So it's 0, 0, 1, 2, x in meters. This is physical space. This is going to be force in newtons, right? So at x equals 0, our force is positive 2. What is it at 2? So I know how to set my limits here. So at 2, 2 squared is 4. So let me, f of 2 is 4 plus 2, that equals 6. All right, f of 0 is 2. So 2, let's say 2, 4, 6. So we start there. we end there. What's it at 1? It's 3, so it's here. All right, so it's a nice, just simple kind of quadratic. All right. When released from the origin, how much work is done in moving the particle from x equals 0 meters to x equals positive? So release at the origin, that means the initial is 0. All right, so work equals integral of force with respect to position. All right, so it's the integral of x squared plus 2 dx evaluated from 0 to 2 meters. So it's x cubed over 3 plus 2x from 0 to 2. All right, so it's